Bueno, pues buenos días a todos. Muchas gracias por venir. Por supuesto, muchas gracias a David por venir. Esta iniciativa hasta donde yo sé el primer acto de algo que por lo menos yo he definido como Mathematics for Quantum. No sé si tiene sentido, pero bueno, por lo menos mal no suena. Y entra dentro de las actividades del EHU Quantum Center, que no sé si muchos sabéis que existe. Es un centro que se ha creado dentro de la iniciativa ICUR, que es la iniciativa de ciencia del gobierno vasco hasta, en principio, el año 2030. Entonces, esta iniciativa tiene distintos pilares y uno de ellos, posiblemente, si no el más importante, desde luego, dudo que haya otro más relevante, habrá otro igual, que es de Quantum Technologies. Y, bueno, entre otras cosas, matemáticas en esta iniciativa no existen, o por lo menos no aparecen, y soy de los que opinan que las matemáticas se van a necesitar. ¿De acuerdo? Lo que no está nada claro es qué matemáticas son las que se van a necesitar. Y, bueno, esto lo he estado discutiendo con distintos miembros del EHU Quantum Center. Perdonad el rollo, pero me parece importante, Y, en particular, con Enrique Rico, que es con el que estamos organizando este curso, y creo que es una oportunidad para este departamento, el Departamento de Matemáticas, desde luego para la facultad, el intentar saber cuáles son las matemáticas que se necesitan para el mundo cuántico, porque no sé si ya se puede llamar mecánica cuántica, en el año 2024. ¿De acuerdo? Y como Enrique y yo no conseguíamos acabar de ponernos a hablar el mismo lenguaje, pues entonces decidimos echar mano de alguien que nos pueda ayudar a entendernos, y Enrique sugirió a David y, por supuesto, me pareció que era la persona adecuada. Y esta es la manera en que le voy a presentar. Si queréis mirar su currículum, solo tenéis que meteros en internet, y lo primero que aparece, hasta donde yo sé, es que le dieron el premio Sabadell en el año 19, por ejemplo, y tiene una cita de Masculel que llama la atención. Masculel es uno de los grandes popes de la ciencia en España, y bueno, pues os animo a que la leáis. Y con esto acabo. Se trata, por lo tanto, de por favor, tomároslo en serio. Dentro del departamento esto es muy importante, dentro de las matemáticas en Beckham esto es muy importante, y al mismo tiempo es apasionante, porque no está nada claro que las matemáticas que se necesiten estén hechas, con lo cual, pues, hagámoslas. Y nada más, muchas gracias.
Gracias, Luis. Bueno, pues muchas gracias a Luis, a Enrique por la invitación y la hospitalidad, y bueno, a todos por venir, que la sala está muy llena, lo cual siempre es de agradecer. So I will change to English now. So first of all, I would like to know, because this is a bit... maybe... No, o sea, sin problemas, esto es lo único. Esto aquí. Sí. Okay, so I would like, I mean, it's a bit of an experiment in the sense that maybe there is a mixture of communities here, so maybe there are people working already in quantum computing, and maybe there are people that know nothing about quantum computing or even about quantum. So I would like to know more or less about the background. So is anyone, I mean, is for anyone this the first kind of exposure to quantum in general? Or, okay, good. So then I will start from scratch, and that's it. So I apologize then for everyone knowing quantum and quantum computing, probably the first hour and a half or 2 hours, maybe this first session will be very boring. I will try to compensate in the next one. So, okay, so just So the first slide, I mean, I will do most in the Blackboard. I have some slides prepared in case I have to speed up to arrive at the end of the course. But that's the idea is to go to do Blackboard. So okay, so I forgot. So this is just to acknowledge the people that fund us, in particular Quantum Spain, which is an initiative at the national level to promote quantum computing, and all the people funding that. Okay, so the plan of the lecture is, okay, start just by introducing the RAC notation, which is just linear algebra, but with a different notation, so it should be totally straightforward. But it's nice to become used to the notation, because otherwise it's going to be hard to follow the lecture. I will also go through the postulates of quantum mechanics, and then I will, so this of course is very well known for everyone working in quantum computing, and then I will go into more or less the idea behind the course, which are functional inequalities, and I will introduce them in the single particle case. So what is called the log-Sobolev inequality, modified log-Sobolev inequality, hypercontractivity, and Poincaré inequality, which is equivalent to what is called a spectral gap. Just to introduce the ideas, we will focus mainly, if not only, in MLSI and gap, and in particular in gap, because as I will comment later, all known ways to prove MLSI, I mean, all these, by the way, this is in the quantum regime. So of course, these things exist classically, but we will work with quantum versions of those classical inequalities. Okay, so everything is in the quantum. So almost all known techniques to prove MLSI is just proving gap and then finding ways to upgrade the gap to the MLSI, and I will sketch one way in which this is done, and probably the only way in which this is done so far. And then we'll go to the interesting case, which is the many-body case. We'll have many particles. And for that, we'll have to work and introduce something called tensor networks, because these are very much related to the existence of a gap. Then I will sketch how these two inequalities, gap and MLSI, appear very naturally in many models of quantum computing, and how these proving bounds on the constants appearing in those inequalities are the relevant constants to bound in order to understand how efficient a quantum algorithm is. And then I will finish by, because I would like to give an overview and cover many things. I cannot enter in many details. I will maybe do some proofs, some sketch of proofs, so they will have a glimpse of what's going on, but I cannot do really all the theory. But I would like to finish by sketching a particular result in which all these things come together, which I find nice, and there we can really give a bit more of detail so that you get an idea of how these techniques are mixed together in a particular problem. Okay, so that's the plan. So please interrupt me anytime. So the idea is that you get as much as possible from this. But as I say, it's more like giving an overview with just some sketch of proofs, some small proofs to give you an idea, but that's all I can do. Okay, so let's start with the very basics. Okay, by the way, this is my email. Okay, you can find it in the internet, but that's my email account. So please feel free to email me after the course if you are particularly interested in some particular topic, idea, problem, and I can give you references or a more detailed explanation of the state of the art or something like that. Okay, so first part is linear algebra, but in Dirac's notation, so it's more about notation. Okay, so as in quantum computing, that's maybe also for mathematicians in the audience, everything is finite dimensional. This doesn't imply everything is trivial, not at all, because what matters is so the dimension, which is kind of the number of quantum particles we have, grows. We would like to understand how the corresponding objects scale with that. So it's about the scaling of finite dimensional objects, and bound scaling of finite dimensional objects is a highly non-trivial problem in general. So that's important disclaimer. So okay, so we'll work with a Hilbert space. Will be always finite dimensional and complex. So essentially, C to the D. So a ket is a vector which we can understand as a column vector. So we understand CD as the set of column. If we want to understand things as matrices, column vector. In CD, and the notation is U. Okay, so this is the label. And this kind of ket notation means that this, you want a column vector. So a bra is a row vector, but let's go this way. So if we write, so the bra U is by definition this, and this is the adjoint. So the is the adjoint. Transpose conjugate, no? The transpose conjugate. Transpose conjugate. Conjugate. Okay. So again, another notation. So the bra, which is with this kind of angle to the left, is just the adjoint, so transpose conjugate of that vector. And again, the physicist notation that we will use, instead of putting a star, which would be the standard thing in mathematics, we put this dagger. Okay, so that's again notation. So everything is about notation now, so that you don't get. Okay, so in particular, so for instance, if we have W, and we multiply this by U, so this is W1 bar, WD bar, U1, UD, which is the sum in I, WU bar, UI, which is the scalar product. Again, we go the physicist rule in which the antilinear part is in the first, not in the second. That's of this. And now this is just the product of these two vectors, and now the notation is, instead of doing this, we do that. No? By definition. So when we put these things together, means that we multiply one by the other. And then, in this sense, this bracket notation is well suited to the scalar product, and that's why one of the reasons this is interesting. Okay, so that's, in the end, if you want this bracket notation, everything is just products of matrices. Though the matrices can be vectors, but everything can be done as a product of a matrix. So now we can define the outer product in this, which is the opposite thing. Okay, so let's put this way. W. Okay, which is just multiplying U1 UD by W bar 1 W bar D, and this gives a matrix, no? I will write it. Okay. So the canonical basis index is written as 1, 2, up to D. So just the label are just the numbers 1, 2, 2D. So in particular, no 1 is just 1, 0, 0, etc. Okay. In the case of C2, which is the space of a qubit, the canonical basis in this case is 0, 1. Okay. We start instead of starting in 1, we are starting 0, and that's simply because this corresponds like the bit values, and that's why. So this is just the 1, 0, and this is the 0, 1. What else? Okay, then it's clear now that we can write. So if we write the outer product of I and j, so this is exactly, let me write it, 0, 1, 0, 0, 1, 0, with this is I position and this is j position, and this is just a matrix with a 1 in the position I, j, and 0 in the rest. So this is just the matrix element, so the basis of the matrices, and therefore any matrix A can be written as the sum in Ij of Iij, Ij. Okay, so that's the matrix Aij, Ij. Okay, so we can write it this way. Okay, so we want to expand, and we will do in a basis. This will be like that. Okay. Any questions so far? I'm going too fast for the beginners. Everything clear? Okay, good. Okay, so next, so one of the very important things in quantum mechanics and definitely in quantum computing is the notion of tensor product. And the reason is that, as we will see in the postulate of quantum mechanics, this is the mathematical object describing when the situation when you have many particles, like many qubits in a quantum computer. Okay, so that's crucial. Okay, so again, I mean, I will do it again in Dirac notation, but since tensor product maybe is not something that even mathematicians usually work with. Is anyone familiar with the tensor product? No? Okay, so I will do slowly. So again, tensor products can be defined abstractly as the universal object that linearizes multilinear maps. But I will not do this way because you don't see, you cannot touch what's happening. So I will just define it in the pedestrian way, in a basis-dependent way. I know this is not very elegant for mathematicians, but I will do this way, okay? In the end, what matters are the properties, and the properties are the same, okay? So that's, okay, so, if we have two Hilbert spaces, again, everything finite dimensional, can be done in infinite dimensions too, but since we need basis. So we have two Hilbert spaces, HA, HB. Okay. Then this tensor product is by definition, so the set of linear combinations Ij from 1 to D of Aij, and then I tensor J, which by definition is an orthonormal basis. Okay, so essentially this is CD square if, okay, or D A times DB, if this is CDA and this is CDB. Okay, so given a basis, let's say the canonical basis here, the canonical basis here, we define a new canonical basis and we give it this name in CD square. Okay, that's it. So we can identify this. Okay, we can. Okay, let's define this way. So we can define it. And now with this, we define the following: given a vector V in HA and a vector W in HB, we define V tensor W in the following way as the sum in IJ VI WJ I tensor J. Okay, but of course so VI are the coordinates. Okay. Yes, I define it. By definition, is an object that is by definition the orthonormal basis here. So I define this as an isomorphic to that, and I simply say that there is a basis that I call it like that. And now I will define everything based on that basis. And for that, I have to see how things are expressed in that basis. And they say, okay, now I can define now this object as the object that in that basis has those coefficients. Okay, that's if you want, you can see us working in here. That's it. Okay. I mean, you can see it as a space of matrices if you want, no? With this is row and column. I mean, you can think in so many ways, but that's okay. So and if you want at the space of matrices, so if you see these coefficients, of course, are matrix coefficients, no? Have two indices. So these are the rank 1 objects. So you want to a picture is just a matrix. Okay, so and now with this definition, we have the following properties, and these are the properties that really matter. So again, this is not by far not the most elegant way to do that, but it's the fastest. So the properties one. Okay, so the scalars. Okay, alpha is an scalar. This is an alpha. The scalars can go out. 2. Have the distributive law in both coordinates. In this sense, it's a product. Same for other coordinate. Okay, same for the other. I will write V tensor W plus W2 equal V W1 plus V tensor W2. Okay, so these are. Okay, good. Next. So this is the object. Okay, and then next thing we need is to define. We need to define operators. Operators on HA tensor HV. So we have A, an operator from HA to HA prime, and B, an operator from HB to HB prime, so it can be different Hilbert spaces. Then A tensor B is the operator, is the linear operator that goes from HA tensor HB into HA prime tensor HB prime, defined by A tensor B acting on I tensor J is AI tensor Bj. Bueno, esto puede ser un problema. Me quiero quitar esto, igual tengo que quitarme un poco de calor. Espera, sí, que igual está enganchado, ¿verdad? Disculpa, que tanto. Hacerme vivo. Disculpa. ¿Ya? Genial, gracias. Muchas gracias. A ver, so okay. Okay. Now I will write some properties, but maybe it's interesting to again, people doing quantum knows very well, but maybe it's interesting that I have defined which these objects are, V tensor W, sorry, and what these operators are, but there are many more elements in the tensor product that things of this form. So if you see, no, we can identify, for instance, this as the set of matrices, AIJs, no? Because we identify with the coefficients. These objects are just rank 1 matrices. Okay, so in the space of matrices, there are many more matrices than rank 1s. Okay, so I define what is called elementary tensors are, which is one are rank 1 matrices and the coefficients, but there are many more objects there. And objects which are not of rank 1 type, or tensor product type, will be called entangled when we talk about quantum states and quantum mechanics. And these are very important. So, okay, so I define what these objects are, but the important thing of the tensor product is precisely that there are many more things beyond that. Otherwise, we will be in the usual Cartesian product. This is not. This is the dimension is the product, not the sum. Okay, so same here. There are many more operators acting on the tensor product than operators of this form. But the same as happens here, that there exists a basis of that form. By the way, I didn't say, but I tensor J fulfills that definition. No? There will be basis of this form of any element from here to here, but important to notice. Okay, so let me give properties of this, and in particular one property that rules them all. So the only one that you need to have in mind. Okay. Okay, so properties. Let me keep. So this is 3. Let me keep the number of properties. So A tensor B. Okay. So I define it just in a basis, but precisely by what I erased and doing the computation, it's very easy to show that if this acts on V tensor W, this is AV tensor BW. Okay. Five. Okay, that's important. A tensor B adjoint is A adjoint tensor B adjoint. All these things are trivial to check. I mean, I'm not checking them, it's totally trivial. It means not. In particular, by the way, this implies that if I do V tensor W adjoint, this is V tensor W, because we know that the adjoint of the ket is the bra. Okay, the identity, tensor the identity is the identity. So, and that's the most important one. A tensor B, C tensor D is AC tensor BD. So essentially, this is all you need to have in mind. So that's the key property. So that the tensor product is compatible with the usual product, with the usual composition. Okay. Again, operators I always see as matrices because it's finite dimensional. So tensor product is compatible with the product of matrices. Okay, so that's the key property. So in particular, so what happens is we do V tensor W. Oh, yeah, D, sorry, of course. Yeah, yes. Of course. Thank you. Exactly, so we do V1, W1, and then we multiply to V2, W2. We apply this, and this is V1, V2, tensor product, write it here, W1, W2, which is the, okay, and now I forgot to say that C tensor C is C, so for dimension 1, and alpha tensor beta is alpha times beta. Okay, I forgot to say that in the one-dimensional case, the tensor product is nothing, and just the tensor is just the product of the complex numbers. Okay, so now these are one-dimensional objects, so this is just the product. Okay, so again, this shows that the scalar product in the tensor product is exactly the one given like that for elementary tensors, which is the usual Hilbert-Smith product. Okay, so this can be deduced if you want, just from this property 7. Okay, so that's why it's, and then again from property 7 is trivial. From property 7 and 6 is trivial that the tensor product is also compatible with the inverses. 8. Assuming that you have invertible operators, the inverse so this means should be read as assuming A and B are invertible, A tensor B is also invertible, and the inverse is this. And that simply is trivial, showing that if we multiply this by A tensor B, we get the identity by using that and that. Okay, that's totally trivial. Okay? I can write if you want. So what happens if we do A tensor B times A minus 1 tensor B minus 1? So another way to use 7 by 7, this is A minus 1 tensor BB minus 1, right? Of course, this is identity tensor identity, which is identity by 6. And therefore, this shows that this is the inverse of this. Okay, which is what is written. Okay, this is 6. Okay, good. Okay, I'm close to the end. Okay, one can keep going, but again, since we are in finite dimensions, I'm talking all the time about Hilbert spaces, but indeed, there is nothing except this very particular case in which the scalar product appears. All we are using is the linear structure, so indeed I should have written maybe vector space of dimension d. So there is nothing about the Hilbertian structure here in all that, except in this very particular example. Okay, so that's so. In particular, okay, we can apply this to any vector space. In particular, for instance, we can take HA to be the vector space of operators, of matrices, and talk about tensor product of matrices. Okay, things like that. So we can. Okay, so I will not go more into that. So if at some point something is not clear, I will be back. But okay, so same we did for 2, one can do for n. Same can be done for CD1, tensor CD2, tensor CD3, CDN, okay? And of course, there is a canonical isomorphism in which we can identify this object with, for instance, we can start with CD1 and that, and define it by recursion. And we can do it in any order, and all these things are canonically isomorphic. Or we can define this from scratch in a basis-dependent way as we did, and all these things are canonically isomorphic. So I think there is no need to talk more about that. Okay, so next, normal last of this reminder. Any questions so far? Yes and no. It's important. Definitely is relevant, as long as you keep in mind where you have. So okay, this is yes, it's relevant. So, but let's put it this way. What I mean by order is they can do this, and now this define first this, and then that by recursion. But of course, I mean, the label of first. So I mean, yeah, yes. Exactly. So it's important. Exactly. So again, there is a canonical isomorphism between this and but by order meant the order in which I do the induction. But definitely order matters. So in particular, this is essentially the particle that Alice has, the particle that Bob has, the particle Charlie has, etc. And of course, the particle of Alice is of Alice, not of Bob. Definitely.
Then the reason why A is A.
Yeah. Usually it's Alice and Bob and these things. Yes, that's the standard. Yes, exactly. Yes.
Are not become. Oh, sorry. I finished the.
So yes.
It's on. Okay. So I finished my question.
Yes.
Already.
Yes. No, in infinite dimension, most of the things are true. One has to be very careful. In infinite dimension, usually you would like to have some usually to have some object which is a Banach space, so that you have a completion, so something that's complete. So you have the algebraic tensor product, that's okay, but you would like to complete it. There are several ways to complete it that are not equivalent. Okay, even of course for the case of Hilbert spaces, there is a unique way to complete it, to have a Hilbert space. But in particular, if you have the objects are not Hilbert spaces by Banach spaces, for instance, if you are tensorizing algebras of operators, infinite dimensional operators, then there are several ways to tensorize these things and complete that are not equivalent, give different objects. So the problem is much more subtle. Of course, you see this also in the finite dimensional case, in the sense that there are several tensor norms that you can put in the tensor product that already finite, so that are compatible with the tensor product, meaning that for elementary tensors give the product of the norms. The same for the duals. but they are inequivalent. And this is all the theory of tensor norms. That is also very relevant for quantum computing, in particular for more like quantum information theory and quantum cryptography. And this is just would be another nice lecture to talk about. I've worked a lot on that, so but it's not the topic of this lecture. But there's a whole thing of, so if you would like now to add a notion of distance in the tensor product, there are several inequivalent ones, and some of those have an operational meaning in quantum information, and understanding them, bounding them, give insights on how robust a quantum cryptographic protocol is, or other things. So it's a very relevant question. Yes, one can do this, but in several ways. Let's put it this way. Yes. More questions? Okay, good. So, okay, so now, yes, let's go to, again, properties that are highly non-trivial in infinite dimensions, like the spectral theorem and all these things, but infinite dimensions is everything is trivial, but nevertheless, I will write them because I need to introduce the functional calculus, which also, of course, is true in infinite dimensions, because I needed to define things like entropies. Okay, so. Okay. Okay, so that's good. The goal is to define functional calculus for normal matrices. A is normal. I guess this is well known to everyone, but again, let me just, if A commutes with a joint, self-adjoint or Hermitian, which of course in finite dimensions is the same. If A is equal to a dagger, unitary, if a dagger is a dagger A equal to the identity, and semi-definite positive if well, okay, okay, you know what's this, and definite positive I will write it like that. Okay. I will not waste time on that, but I mean the notation I will use because that's very important. Okay, so as you know, there is a spectral theorem. Again, for matrices is trivial, that's linear algebra. So for any normal matrix can be diagonalized in an orthonormal basis. And in our language, this is the same as saying that there exists, and this is an if and only if, indeed. Okay, it is if and only if. And in our language, we say that A is normal, theorem if you want, spectral theorem. If and only if there exists VI orthonormal, so that A is equal to the sum in I of lambda I, VI, VI. Okay. Okay, so, and that's again a nice way in which this bracket notation enters is that we can define when we have normal matrices and the diagonalization is in orthonormal basis, we can write A in this notation in terms of that basis like that. then the diagonal structure is totally clear here. Okay, so that's okay, so that's the same as this, but in our notation. Okay, and again, it's trivia. There's nothing. Simply say that. So, for instance, if this would be the canonical basis, it's clear, no? So, then put it, what is the matrix? Again, as a way to play with our notation, this matrix, as we say, the matrix elements ij tell us in which is the coefficient in the position ij. So there is no off-diagonal elements, so everything is ii. So this means that only the diagonal elements exist, and the rest are 0. So if this would be the canonical basis, this is exactly diagonal. Now the same happens for any orthonormal basis, okay? And that's very easy to see. Okay, so good. So finally, we can define the yeah, sure.
We are thinking in high dimensions.
Yeah, exactly. Of course. Yeah, yes.
This thing being computed in the sense that okay, there is in the matrix you have the eigenvalues, but do I have to compute them? Do I have to think in terms of?
It's a very good question. It's a very good question because we will see the whole point of quantum computing, at least of many of the equivalent formulations of universal quantum computation, in the end reduced to the property of estimating the lowest eigenvalue of an Hermitian operator. So the ground state of a Hamiltonian.
I don't want to compute one eigenvalue in the middle, or properties in general.
No, of course, no. These are very relevant too. Of course, yes. For instance, yes, true. No. There are several. Of course, the minimal one is very relevant because many problems can be casted in that way. But for instance, also thermal averages, so the expectation value of a thermal state, and then there, of course, all the eigenvalues enter, though of course via some exponential. But there are quantum properties, like what is called quantum scars, is a new quantum effect that was discovered like not that many years ago, 2-3 years ago. And things that happens is that about the dynamics of things that happen in the middle of the spectrum. And this is still, I don't know if it's well understood yet or not. So no, there are many things.
Do you care about the basis at all?
Again, in many cases, the basis is the eigen. So is so we have some Hamiltonian. These are the eigenvalues, the eigenvectors. So these are the energy levels of the quantum system, and these are the corresponding eigenstates. So by definition, essentially, the basis that diagonalize the object.
Yeah. Do I have to compute it? I mean,
No. Again, as we will see, in some cases, it's very relevant or interesting to compute again the eigenstate of one particular interesting eigenvalue, like especially we care about the low energy ones, so the smallest ones, the very smallest, which is the ground, but also the elementary excitations or low energy excitations, and having good approximations of the ground state or low energy states is very, very relevant. Yes. But again, this is in the many-body regime where we care about these things. I mean, I will come to that in this. I mean, whenever we go to the many-body regime, feel free to re-ask the question. Maybe I can give more details there. But let's say in general, we care about both lambdas and v's, but usually for the smallest. So if this spectrum, usually the density of eigenvalues goes like that, so we care about essentially only what happens here. Okay, in most problems, or here, which of course is. But for the middle, yes, for these quantum scars, I don't know. I don't know, Enrique, you can say more about that. I mean, so or maybe, yeah, physicists in the audience, please.
as usual, it's problem dependent. So in quantum info depends. If you are doing quantum phase estimation, which is basic for many things, in essence, you are trying to look at all the eigenvalues. If you are looking at things like quantum chaos, actually you don't care so much about the tails. You actually care about the shape of the distribution of spacings of eigenvalues. If you are looking at phase transitions, you might care a lot about the structure of the ground state, not so much about its actual fine details, but about how it behaves. Depends very, very much on the question. So that is absolutely right. In many applications, it's simply the lowest lying eigenvalue of a particular operator, which is a distinguished operator. But you might, so it very much depends. Normally, you want information about those quantities, much more than detailed computation. It depends very much on the physical problem you have at hand. I think that's complementary to what you were saying.
Maybe another thing that come to my mind that also may be relevant, or is that sometimes it's relevant if you have this and you do some small random perturbation, what happens? These things are very relevant, very, very relevant. This is called the disorder case, which is what happens in practice. And there are very few things rigorously known in this setup. On this, so how things change under random small perturbations. This is. Again, this is solved by Anderson. The single particle case already in the many body. I don't know if rigorously there are some things, but they're still only in 1D, and I don't know if the proofs are considered complete or not. I mean, still, there are many things about that. Okay, so yes, functional calculus, end of the story then. So now, because if I have that, now if I have a function from the complex numbers to the complex numbers, I can define FA as sum of F lambda I VI. Simply, I apply the function to the spectrum, and that's it. And of course, if F goes from reals to reals, I can do the same. I can do FA if A is Hermitian, because Hermitian matrices have real spectrum. I forgot to say that, maybe. Self-adjoint, this is equivalent to the lambda i's being real. Unitary is equivalent to the lambda i's having modulus 1. Semi-definite positive equivalent to lambda i's being bigger or equal than 0, and this to be bigger than 0. And of course, what? No, but assume it is normal. Assume it is normal. So I'm assuming always normal, because otherwise I cannot define these lambdas like that with this. So I'm assuming normal, and then the lambdas are those coming from the normal below, because all these are particular cases of normal matrices. So all these are particular cases of normal matrices. But you are totally right, of course. Yes. Sorry. Okay, good. So again, so if I have a Hermitian, then I can do the same for function from reals to reals. If I'm semi-definite positive, I can do the same for functions from the positive to positive, etc. Okay, so this is because at some point we will apply a logarithm to positive matrices, which can be done, of course, because the logarithm is well defined in the positive real. Okay, etc. Okay. Okay, again, for instance, or let's put this way, we'll do that. So an example is I can define if A is strictly positive, I can define log A without any. Log means the in E basis, or the Neperian logarithm. Okay. And that will be very relevant for us. Okay, good. I think that's it for this kind of Dirac notation crash course. Any question? Yes.
Yeah, if you want to compute this, wait. Yes. Yeah. Yeah. Okay, so for instance, if you want to compute the square root of a matrix, how do you choose it? Because there are two to the n options, yeah,
No, but
depending on the
again,
sign you take.
yes,
or-
yes. But if the matrix is already okay, yes. Okay, there is a particular way to take the square root of a matrix if it's semi-definite
or
positive,
in general, yeah, there
which
are,
is
yeah,
taking the
different
square root of
options, yeah, to
square root of
define
that.
things, yeah.
I don't know. So is there more than one option to define the square root of a matrix?
Yeah, I mean, a matrix such that when you square it, yeah, when you square, you recover the original matrix. You have two to the n options. Yeah, for instance, if you take the identity matrix 1, 0, 0, 1, then you can have 1, 0, 0, 1, and a plus, minus,
sure,
plus,
sure,
minus.
Sure.
So
No, of course, but there is only okay. I got it.
So,
No,
I mean,
but
you
there is
have
one
so how do
keeping.
you-
Sure,
yeah.
sure. I see the point. No, of course. In this case, there is only one square root, so that the square root is also positive. Because in that case, it's not positive. Of course, it's like minus 1 squared is 1,
Yeah.
which is what happens in
with
those
the
matrices with the
other-
eigenvalues plus ones and minus ones. Of course, if you square, you get all
Yeah.
ones. But no. But if you ask that the square root is also a positive square root, so
Yeah, okay.
it has
And
it's
with
also a
the other
positive
options,
matrix.
yeah, you do it in the same way, yeah. With
So at least this defines a way to define a square root that maps positive matrix to the square root of that being also positive, and is well defined via the spectrum. Let's put it this way. So whether there are other ones.
If you have a multivalued function, then you are defining a multivalued function of the matrix as well, in the same way. So you are defining, if you have branches,
Yes.
then it's exactly the same way. Yes.
Exactly, but if you impose it to be positive one, then it's uniquely defined.
It's as I said, you have to choose it on the beginning. If
Yes. So again, I'm defining the square root. Yeah, exactly. So once you define the function, is uniquely defined. But if there are several ways to define the function, then there are different functions. Let's put it this way. That's it. Yes. Okay. So probably that's the best answer. Thank you. Yes. Okay. Any other question? Okay. If not, let's go now to quantum mechanics, the postulates of quantum mechanics. Again, I will do them only for finite dimensions. And of course, it's true that for some applications of quantum information theory, it's important to go to infinite dimensions, especially if you want doing quantum optics or other things. But since this is just quantum computing, this is just finite dimensions, and I will stick to finite dimensions, and I will avoid things like unbounded operators and all these things. Okay, so okay, postulates of quantum mechanics. For quantum computing purposes. Okay. Okay. Postulate 1. And for those that know all that, just at the end of the postulates, I will start introducing functional inequalities. So maybe you get something new at that point. Okay, maybe. So okay, so postulate 1. So a quantum system is a Hilbert space in our case, finite dimensional. So the state of the system which is somehow the mathematical object which describes all observable properties is an operator, it's rho, it's an operator on H, rho, which is semi-definite positive and has trace equal to 1. Okay. Okay. We say that the state is pure if it has rank 1. If it has rank 1, if and only if rho is of the form psi for some unit vector psi in H. Okay, so this is rho is the orthogonal projector onto the line defined by psi, the space defined by psi. And now, in that case, we do some abuse of notation. So essentially, rho is the same as psi up to an element of modulus 1 to a phase, no? So if I multiply psi by an element of modulus 1, alpha psi, if I do alpha psi and I do the opposite, which is alpha psi adjoint, remember that the bra is the adjoint of the ket, so this is the same as alpha bar psi, and this is 1. So it's the same object. So essentially, and that's the only freedom, essentially. If rho has rank 1, is given by psi, and we have the freedom of change psi by alpha psi. So that's the freedom we have. But that's the only freedom. So then abuse of notation is that we identify rho with psi, okay, in the case of pure. Just forget about these phases. And we say that psi is a pure state. And we say that, say that pure states are unit vectors in H, okay? So we can say that a pure state is a unit vector, meaning that indeed there's an equivalent relations, which is just if you want the projective space, what matters. But okay, so that's the first postulate. The second postulate is the one about the tensor product. Any question? Yes, of course. Exactly.
If you insist on, these are perfectly fine for the finite dimensional case.
Yeah, definitely.
But if you go to the infinite dimensional case and you start from here, you are going to get into deep trouble. Okay.
This course is about
In
finite.
the
but
message. Yeah,
just-
sure.
Let's leave from now.
Exactly.
No questions about infinite dimensions.
Exactly. Because there are several ways in which we can do the infinite dimension. We can start with the algebra of observables and then define the states as linear operators which are self-infinite positive. But then, of course, you have trace or not. It depends if the von Neumann algebra have a trace or not. You have type 3. I mean, a whole thing. Of course, started by von Neumann when he formalized quantum mechanics. So that's why they are called von Neumann algebras. But this is a totally different course. I'm not the right person to give it. So in any case, probably here you have experts. No, usually, no. Gauge invariants are different things. Yes. No. It's just simply a standard use of notation. That's it.
This is a projection.
Sorry?
Irrelevance of global.
Irrelevance of global phase, exactly. If you want, yes, that is global phase. Yeah, but yes, no, it has no name. No, gauge freedom is a very different thing. Sure.
Not a definition or terminology.
It's a very good question. I don't know. I'm a mathematician. For me, these are the rules of the game. So in particular, again, physicists in the audience, please correct me. So essentially, the key of this postulate of von Neumann postulate was to realize that no matter which is the setup, these things are valid. For instance, if you are working with, I don't know, light, and then there is you can define some Hilbert space there, which is maybe, I don't know, the polarization or something, and there you have some measurements, and blah, blah, and all these things are true for a particular Hilbert space that has a physical meaning, a particular set of observables that has a physical meaning, etc. If you work with supercomputing circuits, again, there's another Hilbert space, but there is always a Hilbert space, there is always tensor product, there is always, etc. So, and then this is a mathematical abstraction that if you allow you to work mathematically with these things, but of course, if you want to then use whatever you get in a particular physical platform, then you have to identify, okay, what is the Hilbert space, what is the basis, what is the blah, 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 blah. And this allows to work like abstractly in a way. Why postulates? It's a good question. I don't know. Maybe it's not the right name, but okay, let's stick to that. Yes. Okay, so it's like the rules of the game, if you want. Yes.
Okay. About the now I mean, it's
Yeah, sorry, I erased it.
yeah,
Sorry,
but,
yes.
But it's the state of the system is an operator on H, like rho, and you said it's a mathematical object that describes all observable properties. But with the observable, what do you mean?
Exactly. No, this is part of the other postulate. Essentially, we will see that whatever you can do in the system, so evolving in time, measuring and obtaining information, everything are mathematical formulas that only involve rho.
Okay.
And in this sense, rho is all you care about.
Okay.
Because but again, this doesn't have any meaning until I put all the other postulates.
Yeah.
Exactly.
Okay.
Yes,
because
yes.
then you can, of course, define all other observables that you are interested in measuring and use the rho to extract information.
Exactly.
Yeah.
So essentially, rho is what appears in all the formula to understand how system time evolves or how you measure, blah, blah, and therefore everything is there. There is nothing which is not in there that gives you anything, and that's why this is all you care about, in a sense. Thanks. Okay, good. I'm running out of chalk. I don't know if... Oh, thank you, thanks. Okay, good. Postulate 2. Okay, so if a quantum system okay. Well, if a quantum system is made out of two systems, A and B, the global Hilbert space is HA tensor HB. Okay, so the global system of understanding two individual systems together as a big system is the tensor product. Now, if a system is initialized in A, respectively B, in a state rho A, respectively rho B, the state of the global system will be rho A, tensor rho B.
The question of the phase is still true because it is the tensor.
Is the tensor product, and yes. And again, we know that the phases go out because of one of the properties of the tensor product. So again, this is okay. You can define pure states as tensor products of pure states. It's a very good question. I don't know if he talked about that or he simply talked about commuting observables. I don't know. I read that book at some point, but long ago. We can go to that later. We can go. In Dirac's book is okay.
Which book?
In the Dirac. In any case, it's a good question. I don't know if he only talked about commuting observables, but in any case, for finite dimensions is equivalent to that. So. Okay, so okay, see, good. Now one can. There is another way. So let's see. So now, imagine that this is a particle that Alice has, and this is a particle that Bob has, and then Alice creates in her lab state rho A. Bob creates in his lab state rho B. The joint state is rho A tensor rho B. And for that, they don't need to interact. So they can also do that by interacting classically. Meaning, so they toss a coin, and they communicate the outcome of the coin, and so in a sense they have some probability distribution, and based on the outcome of the probability, they decide to construct at least one particular state above another particular state. So they also require no interaction, no quantum interaction. So the convex, so essentially a state of the form, which is a convex combination of states of that form, of the form and I rho AI tensor rho BI, or BI, with this is lambda I is a probability distribution. These are called separable. It's called separable. And again, these are the states that can be realized without any quantum interaction. All other states are called entangled. And entangled states are those in which to create them, you need that the system A and B interact. Okay. So again, as we know, in this tensor product, there is many more operators, like these ones. So all other states, so a state is entangled if it's not separable. Entangled if it is not separable. Okay, good. Okay. Now, again, so imagine that Alice and Bob So now take a state, rho AB, in system HA tensor HB. So imagine that the state of the global system is rho AB, but now, and Alice has essentially whatever, I mean, his particle still in her lab, both the particle in his lab, even though the state maybe is a entangled one. But Alice can only measure in her lab alone. So in a sense, she doesn't care about the part that is kept in Bob's lab. So then this is the reason to introduce the notion of reduced state, because it's the state that, even if the global state is this, the state that encodes all property that Alice alone, without any help from Bob, can obtain from this global state. Okay? So the reduced city matrix, or the reduced state in system of rho AB in system A, and the same for the other system, is rho A, which by definition is identity in system A, tensor trace in system B, applied to rho AB. Okay? So you take rho AB and you apply the trace in system B, and nothing in system A. And this is, of course, because the trace goes to the complex numbers, this which is a state in the Hilbert space of Alice alone. And rho A encode all properties of the global system, rho AB, that Alice can measure. Okay.
In the case in which they are separable, this coincides with
No, okay. One has to be very careful, no, because here there are several states, rho AI. So of course, if they are a tensor product, definitely it's true, because this is already a convex combination of things. But in the tensor product, definitely, where is the tensor product? Here definitely is true, because if you trace that, this is 1, and then you get that. Okay. Yes. Tensor the trace, TR, the trace. This is the trace in B. Okay, I mean, you need something which is trace preserving, because this has trace 1, this must have trace 1, because it must be a state. Why the trace? Why not? I don't know. This is how it is. I mean, maybe. Exactly. So let's put it this way. So in order to, thanks. I was going to say exactly that. So in postulate 3 or 4, I forgot which order I gave. One sees exactly that. No, how when we say that property that you can observe, we have to show which are the formulas that appear when you talk about things you observe. And in all these formulas is the trace of a state times something. So of course, if this times something is something in Alice, then it's clear that by putting the trace here, I mean, things commute and you get that. So maybe I'll go back to that then, and then it will be very clear that that's the case. So exactly, that's probably the best way. Yes, exactly. It is, yes. This is what it is. Yes. Yes. Yes, yes. In this case, because we are considering the algebra of all matrices, so of course you don't need to. So it must be the trace. This, yes. I mean, this corresponds. Let's put this way. So if, maybe the best thing is if so diagonal. So if we consider only states which are diagonal, these are exactly probability distributions. And then the trace is just summing. And then this is just taking, so if this is a probability distribution on systems A and B, this is the marginal distribution on A, exactly. Probably this is a way to see why the trace, because if you consider the case of probability distribution, which is a particular case of taking states just diagonal objects, this is just the marginal. And then the marginal is exactly what captures that, no? Sorry? Of row AB that Alice can measure. Alice. See, okay. Sorry. Yeah. That system A. That. Sorry. Yeah.
A is Alice and B.
Yes. So no. Yeah. Sorry. This is something that I have in my mind all the time. No. But that's true. Yeah, I'm not a mathematician, but I've been exposed to physicists too much. Maybe. Sorry? No, C is Charlie and E is if, and that's it. But okay, yes.
Here it's Alicia and Peña.
Oh, okay. Nice. Okay, so maybe we should do Euskera names. Maybe they're nicer. Yes. It's a good point. Okay, so again, so maybe again I should have said that in all these postulates, if you take these states diagonal objects, these are probability distributions because they are diagonal matrices which are semi-definite positive, means that all elements in the diagonal are positive, and having trace 1 meaning that they sum up to 1. So this is exactly a probability distribution. And then this notion here is exactly the one of marginal. So the one of a joint, I mean, this tensor product is telling that you have a joint distribution, is exactly that. So you have distribution with indices ij, and that's a joint distribution. And this is the marginal distribution. So in this sense, this is, if you want, non-commutative generalization of these objects in probability theory, done only for discrete probabilities. Okay, so but that's the same. Okay, good. Postulate 3, measurements. Now maybe things become clearer. And I will do only observable. So I will not do POVMs and all these things because I will not need them, I think, in the rest of the lectures, and to avoid extra complications. Okay, so postulate 3. Measurements. An observable in a system is a self-adjoint operator in the space of the system. If the system is in a state ρ, and we measure observable A, the expected value obtained, or the obtained expected value of the measurement is the trace of row A. Okay, and this is why everything becomes clear, because we see that at least for the measurements, the only thing that appears is row and a trace, and that's why this explains why trace here, because now the observable is only made by Alice. So now, if we are in a joint system AB, and Alice, too many A's. Let's call this observable O. And Alice measures observable O sub A. In the global system, the observable is row A tensor identity. And now this and this explains why this. Okay. Of course, one can do more elaborate postulate 3, introducing measurements based on orthonormal basis or POVMs, and talk about the post-measure state and all that, but I will not need that, so I will just skip it. Okay? Any questions? So it's very simple. Observable self-adjoint, and this is just the duality between operators and trace class elements via the trace. So the standard duality. The states are elements in the trace class, but it's for those who are familiar to that, because they are just operators which are positive with a bounded trace, so trace equal to 1, and these are self-adjoint operators with the usual operator norm, and one is the dual of the other, so this is the dual of that space, and this is just the duality is implemented by the trace, which is exactly this. So that's if you want. Observables are dual objects to states, and this is the duality. Okay, so one can even formalize this rigorously. Yes.
I understand that the paradigm of self-adjointness is due to the fact that you want to work with real spectra, no? But okay, it's just the fact that there is a quite trendy community working on non-self-adjoint operators in quantum mechanics, which are Hamiltonians enjoying some symmetry.
I don't know. I cannot tell much. Putting here normal instead of self-adjoint would not change much. Okay. Beyond that, I have no idea. It's well beyond my knowledge.
POVMs versus what he has mentioned, POVMs versus PVMs. So the reason for self-adjointness is simply filtering, which we have set aside. It's essentially that if you make a measurement and then you make it again, you get the same result. So in order to have that, you need self-adjointness. If you simply want, I make a measurement and I get probability distributions, then you do not need self-adjointness. You need operators which are similar as to a self-adjoint one, which need not be normal because they are similar. Mm-hmm. So that's associated with the POVMs that he was mentioning, the positive operator valued measures. Okay, so self-adjointness has to do with this idea that I do the measurement, I do it again, and I get the same result. Otherwise, you don't need it. But on the other hand, we never put it in any of our textbooks because of a Stein-Spring dilation. Whenever you have something that is a POVM in finite dimensions by a Stein-Spring dilation, it can always be made into something that is self-adjoint. So you are home scot-free and you can do this and reconstruct everything by simply enlarging the Hilbert space or not. In infinite dimensional spaces, things are, but I will shut up because otherwise...
No, it's true. Indeed, I will talk about Stein-Spring dilation soon, but in the context of evolution, because again, the goal is to do quantum computing. Quantum computing, most of the thing is the evolution, and then it's a final measurement, and then it will not be relevant for all. I'm going to say I kept it simpler, but for the evolution, then I will have to do evolutions which are not unitary, and then time speed dilation will appear, and I think yeah, I think that one can do an analog thing for measurements essentially, which is this POBM setup. But I think, okay, if at some point in some question is needed, I will go back to that, but I prefer to go to evolutions because this will allow me to finally introduce these functional inequalities, which is kind of the beginning of the game. Okay. Okay. Okay, postulate 4, evolution. Time evolution. Okay. Supposed to is that discrete time evolution of a state is given by a unitary matrix. In the space of the system. So if at time equals 0, a state is rho 0, at then time equal 1, or time initial, let's say. Let's write it in that. So if rho final is equal to rho initial, and then we write u daga u, no? U daga u. Okay. Unitary u, and that's the formula. Okay. And let me write here, in a closed system. Closed means isolated. Okay, so that's this is, we are in very ideal case, isolated system, and we are talking a discrete time evolution. So we only care about what happens after a particular discrete time. So essentially, this is why, yes, then do u square or something, but in particular, you only care about discrete times, yes. We will do, continuous times in a second. So it's just, but that's simply so that's why in the standard quantum computing paradigm, the quantum gates are unitary matrices, because they are just, depending on the setup, they are implemented by some continuous time evolution, but when you take some final time, and then you identify this as a particular unitary, and therefore in a mathematical way of thinking of quantum algorithms in the discrete time computation, then one thinks about unitary matrices, and quantum gates are kind of a universal setting which you can generate particular unitary. So that's why this is the case. So what happens for the pure case? No? Because if the system is isolated, maybe we do have a pure state. So if the state is pure, so what happens if rho initial is pure? Let's call in the initial. Then what is rho final? This is u psi in. Yeah, okay, let's put it this way. Su in u dagger. Now I do this, and I do this, no, because taking adjoints is reversing the order you're taking adjoints. The adjoint of this, sorry, the adjoint of this is that. So this is the same as that. But now we see that if we call this C final, this is equal to C final, C final. Okay? So in particular, unitary evolution keeps purity. No? If you have a pure initial state, the final state is also pure. And this is the way in which we define the evolution at the level of pure states in this abuse notation in which I see pure states as vectors in the Hilbert space. Okay? So in particular, for pure states, we have that C final is equal to U times C initial. Okay, that's it. Okay? Okay, so now we can do time evolution. We can make it continuous. Now or not yet? Yes. Yes. And say, okay, now. Now we can try to make this time continuous. And now we will have now precisely as, okay, let's write, no, we will have precisely because if we concatenate two different times, we get evolution of the sum of the times. This should be a semigroup. And also because it's unitary evolution, we can also go backwards in time, so this is even a group. So if this is reasonable, in the sense continuous, semigroup with infinite dimensions, so there is not such many different notions of continuity. So there must be an infinitesimal generator of this group, indeed, and this is called the Hamiltonian, and this we get then the Schrödinger equation, which is the following. So why do we want to do that?
Yes. Why do you want to go from a discrete time to a continuous time?
It's a good question. I mean, in general, as far as I know, again, physics correct me, this is how things work. Essentially, you engineer some interactions in the system. This is the Hamiltonian, and you let time, and the Hamiltonian is just the infinitesimal generator of the evolution, and then you let time evolve, and you stop the time at some point, and this is the discrete evolution. So essentially, in practice, you do backwards. You first start with the continuum, and then obtain the discrete.
For becoming philosophical, but but then you are imposing here time. Time appears.
Yes, you are totally right, and I will make it appear like that. I cannot tell more. Yes, I guess time and quantum mechanics, especially relativistic quantum mechanics, is something which is highly non-trivial, but it's well beyond what I'm able to say. Yes. Sorry. Okay, so in the end, everything to say that one can obtain from here Schrödinger equation, which is Schrödinger equation, which is of course I will not write Planck's constant. It's in the Hamiltonian. This is the Hamiltonian of the system. and this is the continuous time evolution. Evolution of a closed system. Evolution of a pure state in a closed system. And the Hamiltonian, that's the energy observable. So it's a self-adjoint operator, and the eigenvalues are the energy levels of the system, and this is observable energy. And so the energy is what enters into the evolution. So the evolution is governed by the energy, essentially. Okay. Okay, so now what about non-closed systems? Now. And first, discrete time. Okay, so okay, so and now we go to. So what? So if the system is not closed, it's because it's not isolated, and if it's not isolated, it's because there is an environment that together with the system is closed. So environment is whatever that together with the system becomes isolated. So now, we have now rho in the system. S is system. Okay, that's the state we have. And now we have some rho in the environment. E is environment. S system. E environment. Okay. So let's assume that we have the system in a state S, and the environment is some other initial state E. And the system is in a tensor product. So now, this now is closed. So the evolution is some U in the joint system SE, U in the joint system SE. Okay? But now I only care about what happens in the system. Because, of course, I cannot measure the environment. I can only measure the system. So I have to take the reduced density state. So I have to trace. So I have to implement the trace in E, tensor identity in S. Okay? Which is what we had to do. And this is, if we call this initial, this is rho S final. Okay? SMP. We enlarge the system to make it a closed system. We apply the postulate for closed systems, and we take the reduced state to the system we are able to. Okay, so this looks very weird, but there is an abstract way to understand these objects via this Stein-Spring dilation, and that's the following. So now this is a linear map acting on rho S initial. The linear. Okay, it's clear that this is linear, acting on rho, no? The tensor is dealing with something. By the properties of the tensor product, this is linear on that input. If this is fixed and this is fixed, okay, multiplying by matrices is linear, and of course, this is a linear operator. So this is linear. Okay, which other properties does this awful expression has? So the following. So it's linear. T linear more is trace preserving. Okay, that's important in order to map states to states. And that's clear. So if I trace this, that is I'm putting a trace in S here. the trace tensor of the trace is the big trace. If I apply the big trace here, by cyclicity of the trace, the unitary cancel, and I get the trace of that. Since this has trace 1, this is the trace of that object. Okay, I don't know if you follow me. I can do this. So what happens if I do trace of S of rho S final? This is a trace of S here is the same as putting a trace of S here. So it's the same as putting trace of S tensor trace of E of this big expression. But this is just the trace, the normal trace. Trace tensor trace is trace. Okay, so this is the same as trace of U dagger. Again, I'm skipping the parts. And now cyclicity of the trace, this U dagger pass at the other side. U is unitary, U dagger U is identity. So this goes away. Put it U dagger U, the same thing. This is identity. And that's the cyclicity of the trace. So I get the trace of the inner part, and the inner part was this. Rho S initial tensor rho environment. The trace again is the tensor product of the traces. So this is the trace of rho S initial times the trace of rho E, which by hypothesis this is 1. Okay, and then the trace is kept. Okay, so it's trace preserving. But the most important property is that it's what is called completely positive. Let me go to that. T is completely positive. Okay, what does this mean? Okay, this means that T tensor identity as a map from identity in Mn. So this is n times n matrices. This goes from MD tensor Mn to MD tensor Mn. Of course, I can identify this with MDN. Same here. And now this is positive preserving. For all n. And positive preserving means that maps semi-definite positive matrix into semi-definite positive. But it's important that this is not done by T alone. This will be just positive preserving. This must be true for T tensor identity in the matrix of n times n dimensions for all n. It's enough to take n equal to d, by the way, but that's okay. So, or d squared. Okay, whatever. But doesn't need to go to infinity. D or d squared. I think it's d. Whatever. Okay, so, but then it happens for all n. Good. So, okay, so that's also true for that object there. And now the nice thing is this Stein-Spin direction theorem is that T is linear, completely positive, and trace preserving if and only if is as this. It has this expression. Okay? So these three properties characterize having this expression.
Is there a physical interpretation of the completely positive?
Yes, it is. So this is a physical map. You can do this physically. You just take another system, evolve it, trace it, all these are physical. So physical properties must map states to states. Now, if I take even a bigger environment, and I do, which is this one, and I do nothing on that, this should still map states to states, and in particular should map positive to positive objects, because states are positive, so that's the reason. Okay. No, this doesn't keep purity in general. No, not at all. And that's the whole thing, that if you have an environment, usually purity is gone, because part of the system contaminates, part of the purity is in the system. So if you have a pure state which is not product between, so if you have psi between between system and environment, and is not of the form psi system tensor psi environment, which this would be that environment can be destroyed because already it's pure in the system. So this is, you are not in this trivial case, and you have this already, even not evolving the system, just computing the reduced state in S is not pure, never. It's only pure if it's of this form. So even without evolving the system. So okay, so good. Okay, so essentially this is why let me call TP-CP maps trace preserving completely positive. Okay, TP-CP, because writing trace preserving completely positive is too long. Okay, TP-CP. They are also called quantum channels in the quantum literature. So you read, I have a quantum channel. This is exactly a TP-CP map, exactly the same. Okay, and they generalize Markov evolutions in the classical. So essentially, stochastic matrices. So they are the quantum analog of an stochastic matrix. So stochastic matrix is a matrix that maps probability distributions to probability distributions. So this is the analog for quantum states, which are the quantum generalization of a probability distribution. So this is the non-commutative analog of a stochastic matrix. And indeed, many of the things that will come are quantum analogs that are known to be true for stochastic matrices or stochastic Markov processes, whatever, in the quantum regime. So let me see if I can at least go to the beginning of the thing. So just to let me just finish with the continuum version of this. Exactly. So the same as before. Now in continuous time. Yeah, let's see. We will be interested in semigroups. Semigroups T sub T of TP-CP maps. That's the continuous time. Let's say for continuous time. In continuous time, we'll be interested in semigroups. And again, if they are nice enough, so continuous and so on, then we will be interested on elements of that. And L, this infinitesimal generator, is called the Lindbladian. Lindbladian of the system. And now we'll be interested on the convergence properties of these semigroups based on properties on functional inequalities involving the Lindbladian. This Markovian, yes. This is why exactly is because it's TP-CP. So it's exactly semigroups of TP-CP maps. If no, you cannot. Exactly, no, that's true. But okay, it's important in our case that we are semigroups. So essentially that, yeah. semigroups. Yes, definitely. And they are Markovian, definitely. Yes, but it's just being a semigroup and being continuous immediately gives an infinitesimal unit. But this semigroup and TPCP, this is. But of course, there are no Markovian evolutions, but all these are Markovian. As I said, this is the analog of semigroups of stochastic matrices, which are exactly Markov evolutions in the classical case. So that's okay. So this is one of the things we'll be interested in. One of them, and maybe it's time to stop here, and I will start talking about functional inequalities and these things. So this finishes the postulates part essentially. Let me be sure that I'm not missing something important. I think not. Okay, so in the afternoon we will start talking about functional inequalities in the single particle case, which is just one Hilbert space, and then move to the many body particle case and keep going. Okay. Thank you.